Welcome back, everybody. I'm Mckenzie Mark, and I'm here with the Melting Ice Rising Seas Teach-Out from the University of Michigan. Today I'm going to be interviewing Mark Robbins. Mark, could you introduce yourself?
Hi, my name's Mark Robbins. I'm a lecturer in the Earth and Environmental Sciences Department at the University of Michigan. And my research focus from my graduate work was on glacial chemistry, and now some of the things that I teach in the department are about Earth's ice ages and past extents of ice on Earth.
Wow, awesome. So can you tell me a little bit about your field experiences? I know you've been to Greenland and also the Canadian Rockies.
Yeah, so a little bit of background. We're talking about ice in general. So glaciers have an annual cycle. When it's cold in the wintertime and they grow, they accumulate a lot of snow. Then in the summer, they melt. And this is just an annual cycle. And so they get longer in the winter or into the spring, and then they get shorter in the summer. And lots of researchers have looked at what happens in springtime when that melt first starts happening and how that water travels through the system. And not a lot of folks have looked at what happens, the reverse process, as you go from summertime into fall. So that's what I wanted to investigate. And so I had 2 field seasons. I went to the Canadian Rockies, and I was at the Athabasca Glacier in the Canadian Rockies. And I was there from August, September, and October. And I collected meltwater samples from the front of the glacier to then look at how the chemistry of that water changed, to then sort of work backwards to figure out, well, if the chemistry is changing, what does that mean for how that water traveled through the system? Because you can't see the path that the water takes. So I had a field season looking at this in an alpine glacier in the Canadian Rockies. And then a year later, I went to southern Greenland and was stationed at an outlet glacier from the larger ice sheet right at the southern tip of the island, doing the same sort of work. And I was there August and September, collecting water samples, looking at how the chemistry of that water changed in a more scaled up region.
Awesome. Yeah. Ice sheet's a lot bigger. So why is ice so important to the climate?
When climate is cold, like it is today, when we have ice existing on the Earth's surface, it has a really powerful feedback effect for Earth's climate. So a big thing that factors in is the albedo effect. And so if we compare ice to open water, just broadly speaking, even if you don't know anything about ice or anything about ocean systems, everybody can pretty much easily identify that ice is white or sort of bluish, and ocean water is much darker. It's a dark blue, kind of a gray, maybe sort of green. But either way, if you put the two of them together, ice is brighter, water is darker. And that has a really big effect with albedo, which impacts Earth's climate. Because as incoming light from the sun comes in, when it hits that white surface, so whether it's ice or snow on top of the ice, it reflects it off. Whereas in the ocean, if you have the ocean and you're looking at that with that darker surface, it absorbs it more. It's the sort of thing that may not seem initially intuitive, but if you go outside in the summertime and you kick off your shoes and you're walking around, if you walk on dark pavement versus light-colored sidewalk, the dark pavement feels a lot hotter. And that's because the dark color absorbs the energy that's coming in. And so the ocean does the same thing. So when you have ice that covers part of the ocean or a larger extent of ice on Earth's surface, it reflects more of that incoming energy away, and then that energy isn't absorbed by the Earth and doesn't contribute as much to warming. Whereas if you melt a lot of the ice and you have a bigger area of ocean, it can absorb more of that incoming radiation, get warmer, and keep that heat in our Earth system. So extent of ice really matters for how that energy is divided and parceled and moved from kind of one part of the system to another.
Yeah, so just to be clear, a high albedo means that it is a lighter surface, like a white surface?
Yeah, albedo is measured from 0 to 1.
Yeah.
0 is no albedo, 1 is full albedo.
Okay.
And a higher albedo means more reflective. So lighter in color is higher albedo.
Well, when we were in Greenland, we saw like pools of blue water on top of the ice sheet. Do you see those, like, when you study glaciers? Have you seen them before?
I saw some of those when I was in Greenland, and aren't they pretty?
Yeah, they're gorgeous. Out of the window of the plane, it was really awesome to see them on the way to Summit Station.
Did you notice how these puddles or lakes on the surface were only around the edge. As you traveled further in, there weren't as many.
Yeah.
They're limited, so you can see like rock, and then as you travel into the ice, then you get this kind of band of ponds with these really beautiful blue lakes.
Yeah.
And then as you travel further in, there aren't any anymore. And they're transitory features. And they really are lakes or ponds. And they accumulate melt from the surface of the ice. As the ice melts with incoming solar radiation, it makes kind of streams and rivers on the surface of the ice, which you probably saw leading into these ponds. And so they hold the water there, but it's not a stable configuration because if you have, if I had ice cubes in my glass of water, the ice floats, right?
Yeah.
So ice is less dense than liquid water. So if we have on the edge of the ice sheet all this liquid water that's pooled up on top of the ice, it can't stay there forever because it wants to go down because it's denser than the ice it's around. So those lakes exist, and then they catastrophically drain. Like the whole thing can empty within a span of days.
That's crazy. Yeah, I think the other day I saw some sort of headline that some climate activist had swam in one of those glacial lakes.
Oh, wow.
And I was like, that's so dangerous. I wonder if they really, if they know how dangerous those are. So are there differences between ice found in glaciers like in the Rockies and the ice in Greenland?
Sort of, mostly age.
Okay.
So all ice on Earth exists or originates as snow. And I joke in some of my classes, how do you make a glacier? You have to snow more than you melt.
Yeah.
That's it. That's what it comes down to. And if it snows a lot more than it melts, you can grow a glacier faster. If it snows only a little bit more than it melts, you're going to grow it very slowly. But you have to snow more than it melts. And so once that snow falls, it's a couple-year process for that snow to turn into ice. And it happens due to the weight and the pressure of subsequent layers of snow that fall on top. So if you get your first layer of snow, that's just pretty snow crystals, and then you pile a lot more on top of it. And over time, that weight compacts the snow, and it transitions and metamorphoses into glacial ice. And so how that process happens and the rate at which that process happens depends on how much moisture is in the snow and how much it snows. But the overall process is going to happen whether you're looking at alpine glaciers in the Canadian Rockies or outlet glaciers from the Greenland ice sheet. But the big difference between the two is the size, right?
Yeah.
Because Greenland is a very large ice sheet. And so as that snow falls and the ice accumulates and the ice forms and grows, it's kind of like pancake batter, right? Like you pile it up in the middle and then it flows out to the side. And so as it flows out, the ice that's at the edges, that if you go to an outlet glacier like I was at in Greenland, the age of that ice is going to be much older because it formed a long time ago and it traveled further. Whereas if you go to a smaller glacier, like in the Canadian Rockies, for example, that ice, the magnitude is smaller. So it's not as old because it traveled from where it accumulated out to the toe of the glacier, and then it melts.
Yeah.
So it's younger ice. But overall, the process to make them is very similar.
Yeah. I've heard a lot that some glaciers are growing while others are shrinking, and with climate change, it would seem like everything should be shrinking, right? So why is there this difference?
It comes back to the same line. It has to snow more than it melts.
Okay.
And so if you, any glacier, if you increase the amount of snow that falls on it, then you can grow more ice. And so as the Earth is warming, because that is happening, climate is changing and the Earth is warming, which is why most are shrinking, you're correct. But air masses are changing, and some air can carry, as air warms, it's capable of carrying more water. Right now it's really cold outside, the air feels really dry.
Yeah.
When you walk outside in the summer and it's hot, oftentimes the air feels really wet and heavy. Warm air can hold more water. And so as the Earth is warming, as air masses are changing, they can carry more water. And so sometimes that water in the air in the clouds gets routed over glaciers, and so it snows more. And so if you have a place where it is snowing more due to these changing atmospheric conditions, you can actually have that glacier grow. It's not going to grow indefinitely. This is not a ongoing forever and ever process because it's still going to melt. But if that shift happens so that it snows more than it melts, you're going to have a glacier that's growing, even though most are shrinking and Earth is warming.
All right, well, thank you so much for being here and for answering all of my questions.
You're welcome.
All right, everybody. Thanks again for tuning in. This has been Melting Ice, Rising Seas. I'm Mckenzie Mark, and I hope that you guys are enjoying the teach out so far.